thank you for the invitation and the opportunity to speak here. Okay, I want to build baby robots. So what's the meaning of that? I want to build a closed system which exhibits a learning behavior so that it's a physical system, it has internal parameters, and there are behaviors that you like and behaviors you do not like. If you would like the baby robot, to adapt its internal parameters so that its behavior matches what you want. For instance, you want it to walk, or you want it to talk, to learn a language, whatever. So that's what a baby robot is. And so if you want formally to define this, it's a dynamical system. So you have A of t is the internal state of the robot at time t, and you have an evolution equation, A of t plus 1, which is a function, capital F, of A of t, of what the robot sees at time t, x of t, and this is the input signal to the robot, and of a parameter theta, and theta is what I want to adjust so that the trajectories of this dynamical system maximizes something that I'm interested in, such as, I don't know, happiness or mathematical output if you want a robot that writes your articles for you or whatever. And this is also a would-be model of a human brain. Of course, nobody believes that a human brain is exactly that. For instance, it could be infinite dimensional and continuous time. But still something like that. The parameter theta is supposed to be the synaptic strength of each connection between each pair of neurons, and A of t is supposed to be the list of all the activity levels of all the neurons in your brain. And it seems that human brains are quite good at adjusting their parameters over time so that they behave in reasonable ways to optimize, I don't know, happiness or happiness of yourself, happiness of your friends, or whatever. Not always, but most of the time it works. And today I would like to discuss with you the relationship between this and things that we have seen in this conference, and especially 2 points that I think have not really been mentioned so far, which are, in that kind of system you have temporal dependencies. I mean, if you want to optimize your brain parameters, like each day you want to select a behavioral strategy that will optimize your happiness or the happiness of your friends, well, you do not wake up every morning in an independent new IID universe. If you, for instance, you know that your own state today, or the state of the universe today, is influenced by what you did yesterday. For instance, if you had a lot of glasses of wine for dinner, it's going to change something today. And so you have this temporal dependency problem, and it's quite tricky. And most algorithms I know, most efficient algorithms I know, tend to look at a whole trajectory for a finite horizon and then do a backwards analysis that goes backwards in time. And that's obviously not how we do it. As a physical systems embedded in a universe, we only have one trajectory because most of us have only one life, and we cannot go backwards in time most of the time, according to current physics at least. So another problem I want to discuss is you want to tackle that by gradient ascent, usually. So what we would like to do is you have a loss function Lt at t, which is a function of theta or of at, and you want to get to have something like theta gets theta plus or minus, say minus if you want to minimize, the derivative of the loss function with respect to theta. And in this you have a learning parameter eta. And if you think about it in practice, I think it's the most important parameter in gradient descent. Actually, I think it's fair to say that most of the computation time of machine learning algorithms running right now in the world is devoted to finding reasonable values of eta. Because most of the time you have to try. You have to try eta equal 1, eta equal 10, eta equal .1, and it makes quite a difference. So I just want to discuss today two ideas related to two preprints. One is with my student Pierre-Yves Massé about how to adjust, how to find a reasonable learning rate automatically as you go on. And the other is trying to work with Guillaume Charpia. And it's going to be mostly empirical work. I mean, we do not have theorems, but we have mathematically well-constructed suggestions that seem to work well in practice. So I'm just going to share ideas, and maybe, hopefully, some of you will have some brilliant idea to show something, I don't know. Or maybe you will just like it. So I'm going to spend a little bit of time on this learning step size parameter first, and second then we'll go to this full problem of training a dynamical system online. So just take a stochastic gradient descent. Here I am dealing with a Bernoulli model, so I'm observing heads and tails, and I just want to learn the frequency. A very simple problem, and I do it by gradient descent of the log loss, of the prediction of the next item in the sequence. So it's a well-known algorithm, and I just do a simple gradient descent over time, and you will see that the behavior is really, really strongly dependent on the learning rate. And when I say that most of the time spent on computations right now in the world is spent on adjusting eta, that's not a joke. I mean, they really have to try, and they have to try it anew for each new problem, because for each problem the scaling is different, and that takes really a lot of time. Especially if your learning rate is too low, you're going to stagnate, basically. We had an instance of this yesterday in the talk by Gilles, I think. And this is really an important problem in practice. You might say, well, it's because you use a very simple algorithm, you use stochastic gradient. Today we have better than that. We have more sophisticated versions such as stochastic average gradient, or stochastic variance reduced gradient, SAG or SVRG. So this is SAG. This is SAG. For SAG you have theory. You have a nice theory which tells you that if the learning rate, if the function has such and such properties and the learning rate is less than something, then you have nice convergence theorems. So obviously the purple curve, the one with the widest oscillations, well, doesn't satisfy the assumptions of the theorems. But the surprise is that the next one, I think it's the at a 0 equal 1, so it's the one with the second largest oscillations on the screen. It does satisfy the assumptions of the theorem. So somehow the theorem is not telling you what you see in practice, at least in short time. And of course you see that even with SAG, if you take a learning rate that is too small, you will simply have a trajectory that does nothing at all, obviously. This is for...
I'm not sure, but there is the value of the parameter for which it follows the maximum likelihood?
Yeah, but you know. For SAG, I'm not sure. For the stochastic gradient descent, this is true if the Hessian is constant. And here, there is a value of the parameter for which, well, since the close to the optimum, the Hessian is approximately constant, there is a value of eta for which you stay very, very close to the maximum likelihood, but you don't know it in advance. And so yes, there is a precise value that works really, really well asymptotically, but you have to find it. So this is Saga. It's a slight variation on Saga. Actually, it's better. This picture looks bad just because my student put a really unreasonable value of the starting parameters, but the fact is that the value of the parameter that works best is at a 0 equal 1, and you see that it's right next in the list to the one that works really bad. So there is a fine line between something that really works and something that really doesn't work. You want to be off by a factor of 2 maybe, but not by a factor of 10, definitely. And this is SVRG, obviously. For some values of the parameter, it works really, really, really well, at least in dimension 1. Well, most of the time SVRG works well, except you still have the same problem that small values of the parameter, it's the curve you see slightly on the top. It doesn't do anything because obviously when eta is small, you do not move at all. And now this is what we can get with simple stochastic gradient for a range of values of the parameters of the learning rate and for SVRG. By just adjusting the value of the learning rate using some algorithm that I'm going to define right now, and you see that even the value, the purple curve that was filling the whole screen before, now it starts to explode a little bit and then it gets contracted at some point. And this algorithm is pretty simple. It's just a gradient descent on eta. So why not? Pretty simple, except people don't do it in practice. Where is the eraser? So why not use a time dependent? Eta t and adjust at eta t by a gradient descent. Eta t gets eta t minus the derivative of the loss at time t with respect to eta. So what's the meaning of this? You have a parameter, you have a gradient descent on the parameter theta t, and of course the parameter that you have at time t is obtained by the trajectory. It's the value at time t of the trajectory theta t plus 1 equal theta t minus eta t, derivative of the loss function, which is directly a function of theta t over theta. So that's your basic gradient descent. And now, the value of this system, starting with an initial value theta 0, the value of this trajectory at time t is a function of eta. So I can replace here, theta t is actually a function of eta. Or actually it's a function on the whole sequences of learning rates that I've been using. But I'm not going to talk about that right now. And so at time t, if you know how theta t, if you know how your current position depends on the learning parameter, then you know how to adjust the learning rate.
What is the step size here?
Step size is eta. Oh, sorry. The step size here. You need a new step size. And you hope that the dependence on the behavior of the algorithm on the new step size and eta on the meta step size is less than the dependency on the original step size. And that seems to happen in practice, but we have no way of making this remark formal. And in practice, we do this gradient descent over the logarithm of eta so that we can change the order of magnitude quickly. And then the main problem, of course, is computing these derivatives. Because in principle, if you want to compute how your current position depends on your step size parameter since the beginning of training, well, it depends on the whole trajectory. So you have to do computations all along the trajectory. So now the problem is how to compute this derivative. So the first thing you have is you can decompose the derivative of the loss function with respect to eta as a product of the loss function with respect to theta. And this is the gradient, the usual gradient that you use in your stochastic gradient descent, times the derivative of your current value of the parameter with respect to the parameter eta. Simple enough, fair enough. And we have the same problem here. This derivative of the current position with respect to the learning rate depends on everything in the past. But you can compute it online. You take the basic equation of the gradient descent here, theta t plus 1 equal theta t minus eta t times the gradient of the loss, And you differentiate this equation, and just by differentiating this with respect to eta, for a fixed eta, you get that the derivative at time of theta t plus 1 with respect to eta is equal to the derivative at time t with respect to eta minus the value of the gradient with respect to theta, so that's the basic quantity that you use in your gradient descent, minus eta times, well, you use the same trick again. You get the second derivative of the loss with respect to theta times the derivative of theta t with respect to eta. This is how this gradient depends on eta. So you get a homogeneous equation if you set. Is there a way that I can switch off the projector, because I'm not going to use it anymore?
Off. No, I push off.
And so if you set say ht, which is by definition this derivative of theta t with respect to eta, then you have this nice recurrence equation, ht plus 1 equal ht minus the gradient at time t at point theta t minus eta times the Hessian of the loss function at time t applied to ht. So of course in general you do not have access to the Hessian, but here you only need the Hessian in one direction, in the direction h. So that's usually cheap, because either you can do it numerically, like you compute the gradient at point theta and the gradient at time theta plus epsilon times ht, and then you take the difference and you divide by epsilon. But there is even a nicer looking formula, which is to take a larger epsilon, and it should work worse, but in practice it works very well, and it has the advantage of using one less value of the gradient, so you can approximate this derivative, the square applied to ht is approximately the gradient, the usual gradient at point theta t plus epsilon times ht minus the same gradient at point theta t divided by epsilon. And if you choose the right value of epsilon, which is either eta or 1 or eta, I don't remember which, you get a cancellation between this term and this term, and you end up with only one gradient, and that's very nice, because it's twice as fast. So the graphs you saw before correspond to this algorithm, to a slight variant of this algorithm on log eta, not on eta actually, and with an Lagrange scheme on log eta. So that means that alpha is taken to be the root mean square average of the magnitudes of these derivatives over some time period. So, and it seems to work very well in practice. It shouldn't. It shouldn't work. Why? Because sorry.
There were several curves corresponding to several starting values of eta, or
yeah, exactly. So in the last picture you had several values of eta 0, and the main point in the graph was that after, I don't know, 20 steps or so, you converge to something very reasonable, and you follow the maximum likelihood estimator very closely. It also works, I mean, these graphs are for Bernoulli models, but we also try it on a higher dimensional linear regression problem with a badly conditioned Hessian matrix. And also, we are right now trying to use this on neural networks.
what was the value of eta that it was converging to?
The value of theta?
Of eta, just conversion to the eta t.
Yeah, it does converge mostly, yeah.
And to the value that was the good one if you plug it in from the start? Or?
The order of magnitude only. I mean, the optimum eta would be the inverse of the Hessian, or the in dimension 1 that's a number. In dimension something that's the inverse of the Hessian in the direction that you're currently working with. We get more or less close to that within a factor of 2 or 3. So we do not get the exact value, and it shouldn't work actually. Why shouldn't it work? Because just imagine that you are optimizing a deterministic function of two variables like x squared plus 1000 times y squared. At startup you want to have a very small eta, because you have 1000 times y squared, and so if your learning rate is greater than 2 over 1000, then you're going to diverge very violently. So what happens in practice is that you first select a small value of eta, you optimize y, and then at one point y gets very close to 0, and then you start optimizing over x with a learning rate. Since you have x squared plus 1000 times y squared, the ideal value of the learning parameter when you are optimizing x should be around eta equal 1. So you increase eta again, and so you optimize x, but what happens is that the dynamics on y becomes very, very, very unstable. So even if y had been optimized in the previous step to something like 10 to the minus 20, it will explode again in a few steps. But then the algorithm kind of picks up, and as soon as it notices that y is exploding again, it smashes the learning rate again, and you end up alternating between optimizing x and optimizing y. It's a little bit complicated, but it seems to work for some reason. Okay, so any insight in that would be appreciated. And now I'm moving to the other part of the talk, which is how to train dynamical systems, how to build baby robots.
Can I ask a question?
Sure.
I think I didn't understand actually. So ht plus 1?
Yeah.
I mean, ht is a function.
No.
But you take it, you evaluate it at some point. I mean, the gradients, these are...
So ht is the derivative of the current value of theta t with respect to eta taken at the current learning trajectory.
Yes.
So using the current value of eta.
But next you will want to take it at a new point. The trajectory is going to change.
No, I do it online. So I do not recompute the trajectory. The lemma is that at each time, so you have a trajectory up to time t, and ht is by definition, so there is a slight abuse of notation here, because I write derivative with respect to eta, and eta is changing at the same time.
Yes, that's exactly right.
So the statement is that ht is satisfying this recurrent equation. So using this algorithm, you have a value of eta t at each time t and a value of theta t.
Yes.
And my claim is that ht is equal to, if in the past, instead of using eta t at each time, you had used eta t plus epsilon, then theta t would be theta t plus epsilon times ht. And that is true for all time t. So you do not need to recompute the past trajectory. You have at each time a first order estimate of how your current value depends on the past learning rate.
It's more or less like a second derivative. It remember me of this kinetic equation where you have the speed and the true speed, the true position.
No.
We are going to equilibrium, but in different way like that. Hypocoercive dynamics, etc. No? Of course, there is no Brownian here, but maybe you could.
Well, there is Brownian
If your
influence
computation was so
because LT is
clear
stochastic.
that maybe there is a Brownian inside.
Okay, so I don't see it right away, but maybe you're right.
No, I know this was a joke. This is not completely rigorous. Maybe there is a...
Okay. Okay, so now, forget about that. Except I'm going to reuse some of these ideas later. But forget about that for now, and go back to the original problem of making baby robots. So you have a dynamical system. The dynamical systems depends on an internal parameter theta, and you want to learn theta as you go along. And you only have access to one trajectory of the dynamical system, so you really want an online strategy. You cannot try a different theta and start the trajectory again from the start. You cannot do that in life. So there are several strategies to do that. For example, some people take one long trajectory, they take the current trajectory, they chop it into bits of length, I don't know, 20 times steps, and they use an exact computation of the gradient of each bit of trajectory, and they hope that there was not too much correlations between the bits that you chopped, and then you use that to update that. Of course, if you do that, if you chop the sequence into subsequences of length 20 steps, you are not going to pick up any phenomena that have a time span longer than 20 steps. You are going to treat each day as a fully new independent day, independent from everything that happened previously. So, what can you do? So first, maybe I will give you an example of the kind of dynamical system that we want to train in practice. So I'm going to talk a little bit about recurrent networks, recurrent neural networks. So you have this system A of t, which is in Rn. Ai of t is the activity level of neuron I at time t. You have a function, you have a transition function, so I have to define f and theta. So the recurrent equations are going to be aj at time t plus 1 is defined by, so this is of course fj of a of t of an input signal and of theta, and it's going to be defined as some function of, what happens is I take, for each neuron, this neuron has other neurons that talk to it. So I'm going to take a sum over all neurons I that are connected to J in the would-be brain. So I have a graph on my indices A, the indices I, of some linear combinations, some affine combination, sorry, Wij times A. So it's going to be ij, you've got ai of t plus bi, I want to define combination, I want to be able to shift things, plus I want to take my input signal into account, not necessarily for all neurons, but for some input neurons. So you would want to have a linear form, rho dot x of t. X of t is typically a vector and rho would be a linear form, rho I, depending on j, sorry, rho j. And the set of parameters would be the set of wij for all pairs ij, bi, and rho I. And you have a loss function. The loss function can be anything. And the nonlinearity here, so this is a nonlinear function because people want to have some nonlinearities. And usually it's either a sigmoid function, so something like that, or a hyperbolic tangent, which is something like that. But with a different position of the axis. So it's a simple function that doesn't really matter that much for the theory. So this is just to give you an idea of the kind of systems we're dealing with. So the number of parameters of the system is, well, for each neuron you have one so-called bias. You have a parameter for each edge in your graph, and you have some input parameters, typically only for a sub-part of the neuron, like the neurons in your eyes or something. So it's a smaller set. So you want to train all that online without going backwards. So now there are different strategies for that, but the simplest one is, well, let's do stochastic. Well, let's do a gradient descent again. I mean, I have LT of A of t, which is my loss at time t. And I would like to set theta t plus 1, which is the derivative of LT with respect to theta, knowing that A of t is itself a function of theta along the whole trajectory, and that's the main problem. AT depends on theta through all past computations. And so there are strategies for that. Maybe if you come from a signal processing community, you might say, okay, let's do a Kalman filter on instead of gradient descent, let's do a Kalman filter on the pair A and theta. And the main problem with that is that its complexity is like the dimension of A to the 3 or 4, something like that, depending on the connectivity of your graph, and so it's not applicable if you have more than 100 neurons, which I hope we do. So the Kalman filter is out, and anyway, inside the Kalman filter, you have a covariance matrix C theta theta, CAA, C theta theta. And what you get here is exactly C theta theta times this gradient, the derivative with respect to theta of the loss at time t, of AT actually, of the activity at time t. So if you want to apply the Kalman filter, you have to compute this quantity anyway.
So it's theta, like theta t plus eta something like that.
Oh, sorry. And of course, in practice, we also use a substitute for the Hessian here, but I'm not going to talk about that today. So, what do people do then, if you cannot use a Kalman filter? Well, people don't do it online. So, what's happening here? I mentioned that it's simpler to do it backwards in time. It's simpler to have the whole trajectory, to compute the derivative along the whole trajectory, and then to adapt theta and recompute a new trajectory. Why is it simpler? So here is an example. And this illustrates, a phenomenon that's common in a lot of approaches. You have that phenomenon in recurrent neural networks, where the standard technique is backpropagation through time, so it goes backwards in time. You have the same in hidden Markov models, where you have a forward pass in which you compute the trajectory, and a backward pass, which is essentially computing gradients. You have the same in reinforcement learning, when you have the Bellman equation that goes backward in time. In optimal control, you have the Bellman equation as well, and it goes backward in time. So why? Why does it backwards in time? So assume that for simplicity, I'm going to assume that theta influences only the starting point, theta 0, and let's look at the derivative of the loss with respect to A0, and let's compute the derivative of the loss at time t with respect to the parameter, which is A0 in that case. So you will have the derivative of the loss with respect at time t with respect to theta, which is the derivative with respect to a0, and you can apply the chain rule. It's the derivative of the loss at time t with respect to where you are actually at time t, a t, times the derivative of a of t with respect to a at time t minus 1, times the derivative of a at time 1 with respect to a at time 0, and all of these derivatives here, this is your basic gradient of the loss function with respect to the current position, so typically you have access to it, so standard gradient. For the IID setting, and all of this you can read explicitly on the function f, on the recurrence relation. The recurrence relation f is fixed. You know f. You can say exactly how a at time t depends from a at time t minus 1. So that's basically the derivative, the partial derivative of f with respect to a at time at point a of t minus 1. And theta and x, theta t xt. So what do we have here? Here, this partial derivative is usually a matrix in practice of size dimension of a times dimension of a. Usually it's pretty sparse as a matrix because in your graph, well, the neurons that influence neuron j at time t plus 1 are a very small number compared to the whole size of the problem. So usually these terms are sparse matrices, and this, the gradient of the loss at time t, is just a vector, a row vector of size the dimension of a. It's just the derivative of the number with respect to a. So what you have here? You have a product of a vector with plenty of matrices. And the matrices are usually sparse, but not necessarily. So since multiplication is associative, you have two ways of computing this product, from the right or from the left. And if you go from the right, you have vector times matrix, that's a vector, times matrix, that's a vector, and so on and so on. You're happy with that. If you go from the right, then very bad things happen, because you have matrix times matrix, so that's a full matrix. It's much costlier to compute. Times a matrix, times a matrix, times a matrix, and only in the end you evaluate this on a vector. So that's a very stupid way of doing this computation. And what's worse is that if you do it from the right, you lose a sparsity. Because you have a sparse matrix times a sparse matrix, etc., etc., it doesn't stay sparse. So it's really a catastrophe if you want to do it from the right. Except you have to do it from the right if you cannot go back in time. So you have a quick way that goes backwards in time, or a slow way that goes forward in time. And this fundamental reason applies to basically all reinforcement learning-like algorithms. Typically, people do the learning backwards in time. So because it's much more efficient, but it's not. I mean, you could do it forward in time. You could do it. It would be much costlier. Okay. So what can we do? One thing that people do is, I compute a few steps, I go back in time 20 steps, I compute the gradient over those 20 steps, and then I go one more step forward, I compute 20 steps back, etc., etc. And obviously it's more or less the same as what I mentioned before. It works more or less, but you lose any time effect that is longer than 20 steps. So it's people do it in practice, but it's not satisfying intellectually, and you're going to miss a lot of things, obviously, if you do that. So now this was for a particular case, but you see that the object that we need to store, if we want to do the computation forward in time, the object we need to store is the derivative of the current state of the network with respect to past parameters. So define gt, the derivative of a of t with respect to theta. And here the same remark as before applies. It's going to be the derivative along the actual values of theta that have been used in the past. You want to compute this gt. So just to give you an example, I have the example of a recurrent neural network, but I also have another example which is a hidden Markov model. And an algorithm like this has been suggested by Ollivier 2 or 3 years ago, I think. And it was not exactly a gradient descent, it was expectation maximization, but the algebra is really the same. And so what you have here is an object, a matrix of size, the dimension of A times the dimension of theta. And if you apply this to an HAN, for instance, you have to store at each time, for each state of your Markov chain, you have to store basically the number of trajectories that end up at that state at that time, and so in that case, gt is equal to gt is indexed by ajk, which is basically up to a change of variables. It's the number of trajectories of the Markov chains that end up. It's the number of times, sorry. It's the number of times that the edge ij has been used in trajectories that end up at k at time t. That end up at k at time t. So just to show you that this is a pretty big object. And in the current fashion is to say that if you have an algorithm that has more than linear or linear time slot complexity, then you're dead. That's a viewpoint you may or may not share, but it's if you want to have a simulation of a brain or whatever, you want to have something linear. So our problem is here that we have this gradient to compute. And as before, as for the case of learning the learning rate, you can compute a recursive equation for this gradient at time t plus 1 just by differentiating the basic recursion equation, which is not on the blackboard anymore. But if you have a t plus 1 equal f of a t and theta, what you get is gt plus 1 is the derivative of f with respect to a applied to jt plus the derivative of f with respect to theta, evaluated at the current value. And so this is something you could compute if you can afford to store gt. The derivative of f with respect to a, as I said, is a sparse matrix usually. The derivative of f with respect to theta is also pretty easy to compute explicitly if you have the basic equation of your system. And so in principle you can compute gt, except you cannot even store it. So how are you going to proceed? And here comes a very complicated theorem. I'm going to work with one direction at a time in parameter space. So at each time, I'm going to define a current search direction, and this current search direction will evolve stochastically among the possible search direction in the parameter space, but I want to get from this stochastic search direction, I want to get an unbiased estimate of this gradient gt. And once you have the gradient gt, of course, you can adapt theta by gradient descent, theta gets theta minus eta times the derivative of LT with respect to the current state times gt, which is the derivative of A with respect to theta, so you get the derivative of the loss with respect to theta. So the very complicated theorem is the following. It's related to what we've seen tomorrow morning in Nicolas' talk, using the small rank approximation of Hessian matrices and so on. So, remark, if I have a matrix M, and I have a decomposition of M as a sum of rank 1 terms, UI, VI transpose, UI, VI are vectors. I take epsilon I independent, uniform, plus or minus 1 signs. I define U equal the sum of epsilon I UI and V the sum of epsilon I VI. Then U times VT, it's a rank 1 object, it's very simple to compute, and its expectation is equal to M. And the proof, and the proof. Okay? So how am I going to use that? You will notice that the equation, the recurrence equation for GT, my main object of interest, this equation is affine. So it means that if I have at time t a random but unbiased estimate of GT, then at time t plus 1 I can get a random but unbiased estimate of GT plus 1. So now, the corollary is as follows. I'm going to use this decomposition in the recurrence equation for GT. The corollary is an algorithm that maintains a vector delta A in R to the dimension of A, or actually it's a tangent vector of the activity of the space in which the activities live in, delta theta, an object, a search direction in the parameter space, which again is actually a tangent vector. It makes sense in a differential manifold setting. And I'm going to update them as follows. So delta A at time 0 gets 0, delta theta 0 gets 0, and delta A at time t plus 1 is going to be the derivative of f with respect to A applied to delta A at time t plus sum of epsilon I EI. These are the basis vectors for A. A is a vector, and delta A and the signs are taken at random at each time independently, and delta theta t plus 1 is going to be well, the sum of epsilon I times the derivative of fi with respect to theta. That is, the derivative of the ith component of activity at time t plus 1. So this is basically the derivative of ai t plus 1 with respect to theta. And then the statement is that at each time, the expectation of delta A delta theta is equal to gt. Delta AT times delta theta t equal to gt on average. So that's simply by applying the remark to the recurrence equation, because, well, you have gt, you have an approximation at time t, which is delta AT times delta theta t. And when you apply, oh sorry, I'm missing something, plus delta theta t plus, no, this one is correct. So here I'm applying the lemma. The derivative of f with respect to theta is the sum of the derivative of ei times the derivative of fi with respect to theta. So I apply the lemma to the second sum. I apply, for the first term actually, I removed epsilon 0. I would need an epsilon 0 formally for the first term, but you can take epsilon 0 equal 1 without loss of generality. And yes. So it's very simple. And based on that, you can make a stochastic gradient descent on them. Yep?
But the variance explodes.
No. Well, it depends. So I'm using several things. So if your system has a finite memory, then basically you are multiplying delta A by the Lyapunov exponent of your system, so the delta A part does not explode. The delta theta part, with the equation I've written here, indeed, its variance is proportional to t. So there is an additional trick in this rank 1 decomposition, which is to use that ui vi equals lambda I ui times vi over lambda 1, another very complicated theorem. And you can optimize over lambda I. And proposition, the best lambda I is when you equalize the norm of ui lambda I is equal to the norm of vi over lambda I. So you get lambda I equals square root of norm of vi over ui. And this spreads out the contractive property of df over dA over both equally. So if you do that, indeed, the variance will explode. If you do that with the variance trick, and if your system is ergodic enough to start with, I mean, if your system is not ergodic at all, there's no hope of learning anything on that. If your system is ergodic, then, well, technically, if the eigenvalues of df over dA are all smaller than 1, then variance does not explode. You have a stationary process, random process for delta A and delta theta. You also have a continuous time version if you want to play with it. Okay, I should stop soon.
There is no LT, no eta.
No?
Il n'y a pas de LT, pas de eta dans ton truc. Ça...
No, it's just a way of approximating GT, and then once I have an approximation of GT, I update theta thanks to the stochastic gradient descent up there.
So, using eta and LT? No.
Yeah.
But still, there is no equation.
No, LT is not in those equations. GT is the internal dynamics of my system. It tells me how my current state would be different if I had made different decisions in the past. So GT does not depend on LT.
No, but LT should appear in the equation. No, it should not.
No. just the gradient of your basic dynamical system equation. I mean, even if I do not learn anything at all, I still have to compute GT, even if I do not use it to go to update theta. And that's what this lemma does. So that's basically it. And we were very surprised because if you use this, even if in rank 1, if you use this, it seems that we are able to track quite efficiently the trajectory that we would have got using the exact GT. I mean, we spend enough time computing the exact GT for some neural network, and we saw that this algorithm kind of matches it if, in addition to the if you do not use a simple gradient descent, you have to use, as I mentioned before, you have to use some kind of substitute for the Hessian times h t minus 1, and this is a Hessian substitute. Such as ht equals, just like yesterday, the sum over t of the estimates, the empirical estimates using this algorithm of the derivative. Transposed. And by tilde, I mean estimate using this approximation. Okay? You've got a rank 1 approximation of GT at each step, like delta A times delta theta. If you can do rank 1, you can do rank 10. Just by using independent estimates. Actually, you can do slightly better. But in practice, it seems to really work quite well, and we do not have the problem that we rely on finite size intervals that introduce a bias in the gradients, so that we are able to pick up longer time dependencies. Not perfectly, because there is some noise in that, but still, it was quite surprising. So no theorem so far, but maybe there will be some in the future. Thank you.